Hey, we're going to look at a special type of molecular modeling kit, not your friendly neighborhood introductory chemistry one though. So let's really quick, it's called a Molymod set. And it's more useful for general chemistry, I think, as we have a more advanced viewpoint when we look at hybridization, which I don't cover in introductory chemistry, but I do in general chemistry. So we need a better model set to represent hybridization, because what you typically use in introductory chemistry, maybe high school chemistry, is a stick and model set, right? So you have single bonds are represented by these sticks, and you have a couple of atoms and you use a stick, maybe something like this, and you just stick them together. And if it's a double bond, you use springs, and the springs band in a triple bond would be 3 springs and all that kind of fun stuff. And a specific color represents a specific atom. So for example, in introductory chemistry, black would usually mean carbon, blue would mean nitrogen, white hydrogen, red oxygen. That's typically what you do. That's not how a Molymod set's going to work. So here's the 2 main differences between a traditional stick and model set and a Molymod set. So I got a Molymod set right here. Ooh, it's fun. Lots of fun. Colors in a Molymod set represent hybridization, not atoms, specific elements, right? So maybe in intro chem, this would mean carbon. That's not necessarily true in a Molymod set. This would be anything with a specific type of hybridization, and we'll see it's an sp3 hybridization, this one. So whether it's an oxygen, a nitrogen, a phosphorus, a carbon, doesn't matter. If it has that hybridization, and I'll list that up, it's going to use that color. So you might have a model with 2 black balls here next to each other. So they represent atoms with the same hybridization, but they could be 2 totally different elements. Oh, so it's a whole different way of looking at things. So that's a big one. So get color equals an element. Blah, get that out of your brain. It's gone, right? Represents the hybrid. So if you don't know your hybridization, sp, sp2, sp3, sp3d, sp3d2, if you're not real quick on that, you want to review any videos or information on hybridization. Very, very important. Don't even try to use this model set unless you are very, very adept and confident in your hybridization. All right. The other huge difference, like in a typical intro chem set, use springs for double and triple bonds, right? Wang, wang, wang. That's not reality, but it works at an introductory level. It's perfectly fine. For multiple bonds, remember a multiple bond has a sigma bond, right? Head-on overlap between 2 orbitals. And then a multiple bond is a pi bond. You have an unhybridized p orbital on one atom and an unhybridized p orbital on another atom. And those unhybridized p orbitals overlap. So for example, let's say I had something like this. Let's say this is an atom with an unhybridized p orbital, right? Positive lobe, negative lobe. Let's say I have another atom also with an unhybridized p orbital. Review your hybridization, gang. Let's see if I can find a purple one that looks like that. All right. So let's say I have 2 atoms next to each other, and they both have unhybridized p orbitals in the same axis. They can't be in opposite axes. You can't have x and z. They have to both be z, or both be y, or both be x. But can you see those? If they're next to each other, those p orbitals, those unhybridized p orbitals are overlapping, gang. That's a pi bond. That's your multiple bond. Oh, so a sigma bond, right? You can represent like that, right? Or we could use, really we should use a shorter one. Ooh, I hate these little tiny ones. They're so little. Right? So if we represent that as the sigma bond, there's your pi bond right there. So that's a double bond. See the sigma bond and the pi bond there? Oh, head-on overlap between the orbitals, electron density there. Electron density due to side-by-side unhybridized p orbital overlap up and below the internuclear axis. There's your pi bond. So that would be one line in a Lewis structure. This would represent a second line, that multiple bond. And if we had a triple bond, we would just have another set of p orbitals unhybridized in another axis. I'm not going to do a lot of specific examples. I just wanted you to know how to use these and what is represented. So let's show you what the colors mean real quick. All right, what we're going to do is we're going to break up our atoms, right? So you take a look at your Lewis structure and you go, well, is that atom a central atom? or a terminal atom, right? Central atoms have at least two other atoms bonded to it. They're in the middle, central. Terminal atoms are on the end. They're only bonded to one, right? And we know halogens and hydrogen's always terminal. Halogens like to be terminal. Carbon pretty much is always central, at least for us. I guess there's some rare examples where it isn't. And, a lot of times you'll see sulfur, phosphorus in the center. But you can tell just by looking at the Lewis structure. So identify central versus terminal. All right, and then we're going to identify what color to use. So here it is. If it's a central atom, it's going to be one of three colors. All right? It's either going to be black or blue or green. That's it. You only need one of those three, which is kind of like, oh, I'm going to lose that. It's going to roll off my table. So if you look at your Lewis structure, right? And look, if you've got 4 electron groups, it's sp3, right on, sp3 hybridization. So in that scenario, we're going to need 4 holes, one for each hybrid orbital, and that's going to be black. So if you look at the black ones, you have the holes. So 1, 2, 3, and 4. There it is. So we have 4 holes in there. So when you put in bonds, right, or electron groups realistically, right, this could be like ammonia with 3 single bonds in a lone pair, you get 109.5 degree bond angles, and you get that tetrahedral electron group geometry. But for example, let's say we have NH3. We just say we got some hydrogens. Notice there's only one place to stick something there. Hydrogens can't have more than one bond. Right? And then this will just be, so you see the 3 electron groups, and then this, if we pull that out, see that lone pair? We could just leave it blank, an empty hole for a lone pair. Technically what they like to use, whoa, I totally fumbled my lone pair. You'll vacuum that up later, right? So typically they use this to represent a lone pair. So you can see the trigonal pyramid. But a lot of times I hate pulling these little things out. I'll just say, hey, in lab, ripping our fingernails out. We can use this to rip things out. Poop. But I'll just leave it like that and say, hey, if you got a blank hole, that's going to be a lone pair. Unless you really want to take this little connector, that little white connector, pop that in there and pop the lone pair. But that can be harder to take out. Sometimes this little tiny white thing right here, oh man, I can't even grab it. This little tiny white connector, you can't get out with your fingernails. So you gotta slide this on and pull it out. Right? Half of the time you spend in lab putting these together is pulling these things apart. You're like, so the whole lab, you're like, you hear all these things. I still can't find where that lone pair went. There it is. Ha ha, I found you. So anyway, so that's if you're sp3 hybridization. Well, what if you're an expanded octet, sp3d, 5 electron groups, or sp2 hybridization? That's where you get a multiple bond in there with the unhybridized p orbital. Hey, we need 5 holes for both of those. So we're going to use a blue ball where you got 1, 2, 3, 4, 5 holes in there. So if you had 5 electron groups, right, sp3d, you would have those bonds in there. Ooh, getting arthritis in this thumb right here, so it hurts to press. Getting old ain't for weenies. Right? Can you see the trigonal bipyramid? Right? You can see the 3 in the equatorial region there, and then the 2 in the axial region. So it gives you the 90 degree bond angles between axial and equatorial, and 120 degree bond angles between equatorial and equatorial. It gives you the proper angles. So that'd be sp3d. We're going to use the exact same thing if we have sp2 hybridization. So there's the sound all day long. So when you look at this, there's only 2 holes. See, these 2 are not opposite each other. Remember, if you have an unhybridized p orbital, if it's sp2 hybridized, you're using 2 of the p orbitals, but not the third. So you have an unhybridized p orbital. You have to find the holes that are opposite of each other, and then put that unhybridized p orbital in first. Right? This is not a p orbital. That's not a p orbital, right? P orbital has the 2 lobes at 180 degrees apart. And once you put those in first, then you can put your sigma bonds in, right? So you can see the 120 degree bond angles there. You can see the unhybridized p orbital. And if that's next to another one with an unhybridized p orbital, you can see where you get your pi bond. Righto. All right. let's say you have sp3d2, 6 electron groups, or sp hybridization, where you're using one of the p orbitals, but not the other two. So you have 2 unhybridized p orbitals, right? So either of those hybridizations, you're going to need 6 holes this time, and that's a green ball, right? So you've got, if you look all the way through there, you've got 6 holes in that puppy. So if we have, for example, sp3d2, we're going to have 6 electron groups. Let's pop those all in there. That should give us an octahedral geometry, correct? I'm not going to do specific examples. That's what your lab's for. Right? So you see the 4 there, the 1 up, 1 down, 90-degree bond angles everywhere. So that gives you an octahedral electron group geometry. Right? That's why we have the green ball. Or if you have sp hybridization, where you have 2 unhybridized p orbitals. Now these are all 180 degrees apart. Right, so these are a little bit easier than the other ones. So let's put in always put in your unhybridized p orbitals first. So there's one unhybridized p orbital. I'll use a different shape for the other one. Right, so you see, so in the way I have it, I have an unhybridized orbital, a p orbital in the z-axis, and an unhybridized orbital in the x-axis. And then I can put my sigma bonds in the y-axis in this case, coming at your face, but I can rotate this all around that I want. Right, so you have a situation like this. Right, so this has the potential to form a triple bond, right? So this would be the sigma bond to another atom. You could have a p orbital overlap in this axis, in this case the z-axis, the way I have it. And then you could have a p orbital overlap in the y-axis, but I can't show that. Right, do you see that? So you have 2 separate p orbitals overlapping, so for the extra multiple bonds. So it's a sigma bond plus 2 pi bonds. That'd be your triple bond. Let's take a look at terminal atoms. For terminal atoms, we're going to have to hybridize these as well because we need to figure out what color to use. So do the same. Look at the Lewis structure. You know, does it have single bonds, lone pairs? Figure out the number of electron groups. But we're not going to have an expanded octet as a terminal atom. Those will only be central ones, right? So which means we can have sp3, sp2, or sp hybridization. That's it. Those are the only options. So just like with central atoms, right, we just don't have the expanded octet option. So sp3 would be black, right? So anything with 4 electron groups, like typically your terminal halogens that have a single bond, or in this case, a sigma bond, right? So we're going to use these longer ones for sigma bonds. And these dreaded little tiny ones we're supposed to use for multiple bonds. So these would be sigma bonds or single bonds, and these would be for like the sigma bonds and double and triple bonds. I hate these things. Right? These are so much easier. You can pull them out with your hand, right? So typically a terminal a halogen, like fluorine or chlorine or bromine, would have a sigma bond or a single bond, and then 3 lone pairs, 1, 2, 3. And a lot of times I'll just leave it like that, or you can take and put the little gray things to represent the lone pairs. I find that a waste of time when I'm in lab trying to do as many as I can. If I'm just doing one, I'll do it right. But in lab, I'll just be like, just leave the hole. That represents a lone pair in the Lewis structure. So that'd be a terminal halogen, for example. So what if we had sp2 hybridization? So maybe an oxygen, that's a terminal oxygen with a double bond, right? So maybe you got a carbon-oxygen double bond for an aldehyde or something like that. Yo, what's going on with that? Or a ketone, the organic stuff, right? You'll see them in carboxylic acids a lot. You'll have one of the oxygen, carbon-oxygen double bond, and the carbon-oxygen single bond. So we need 5 holes for that, and that's the blue, right? And so again, just like before, you pop in the unhybridized p orbital, and then that leaves you 3 holes for your 3 sigma bonds. Boop, 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 boop. And there you go, and you just connect it to the other one and make sure that you overlap. And technically, we should use the little tiny one for the double bond, and then the other one connects in. So if I let's find the opposite sides here. And it would connect in like so. There's your sigma bond, pi bond. That's a double bond. Boop, 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 boop. That cannot rotate. That would break the double bond. Single bonds can rotate, but double bonds cannot. Triple bonds cannot. Multiple bonds would break if you rotate them. If you have sp hybridization, of course, you need the 6 holes, just like with the central ones. And you put the 2 sets of unhybridized p orbitals in with the sigma bond. That works. Green ball for 6 holes. But hydrogen's always terminal, right? So if you ever have a hydrogen, it can only form, duet rule, it only has 1 hole in it. It can't have lone pairs. So you just stick that on there. Boop. That's how you do a terminal hydrogen. That's a Molymod set. Pretty straightforward, right? So again, using these for sigma or single bonds, using these to represent multiple bonds, right? A sigma bond and a multiple bond, even though in lab I say, oh, I just use that. Easier to pull apart, right? And you're set. That's all you need for the Molymod set. Usually you need to inventory it, right? Because it's amazing how they all kind of get borrowed by, hey, let me grab that. So you're standing next to someone else and somehow your pieces ended up in theirs and it becomes a big mess. So always inventory these before and after. There should be an inventory list, right? So we have an inventory list there. It tells you how many of each. So just check it before and after and have at it. So when you do the lab, now you know what things represent and why we use colors for hybridization and not for specific elements. Haha, we don't use springs for multiple bonds. It is unhybridized p orbital overlap. Molymod sets. Have one at home.